welcome to True Projects. In this video, we are going to see understanding the timing of eruption and using a machine learning approach to classification of seismic time series data. Introduction. It is difficult to predict volcanic activity because large-scale changes in volcanic systems are complex and poorly understood. Accurate determinations are hampered by the absence of a systematic definition for eruption end dates and the gradual nature of some eruptions. Communities living near volcanoes are at risk due to this uncertainty. To address this, operational definitions for eruption end are either generic, such as the 90-day rule without visible eruption signs, or specific to a given volcano, such as seismic tremor amplitude changes. In order to define volcanic states, eruption, unrest, and repose, critical thresholds governing volcanic behavior must be understood. In volcanology, machine learning has become a promising tool for data analysis and real-time monitoring, assisting in the identification of behavior transitions and enhancing volcanic hazard management. Objective of the project. This project uses machine learning to classify seismic time series data with the aim of understanding the timing of eruption end in volcanic systems. The project analyzes a dataset of volcanic eruptions obtained from the Kaggle website using a variety of machine learning algorithms including random forest, support vector machines, logistic regression, and Gaussian process classifier. The project aims to identify patterns and critical thresholds that govern the change from eruption to the end of volcanic activity by examining the seismic time series data, which will improve the management and forecasting of volcanic hazard. Requirements. These are the requirements needed to execute this project. Hardware requirements: operating system of Windows, processor of i5 and above, RAM of 4 GB and above, hard disk of 20 GB and above. Software requirements needed are Python IDL of Python 3.7 version. These are the algorithms used in this project. The first algorithm is support vector machine. Support vector machine is employed for binary classification. SVM is effective in separating eruption and non-eruption states by maximizing the margin between data points in high-dimensional space. The second algorithm is logistic regression. It is suitable for binary classification. It estimates the probability of eruption occurrence based on seismic time series data, providing insights into the likelihood of eruption end. The next algorithm is random forest. It is used for ensemble learning and classification tasks. It combines multiple decision trees to improve accuracy and handle complex data relationships and volcanic activity patterns. The next algorithm is Gaussian process classifier. It is utilized for probabilistic classification. It models seismic time series data uncertainties and captures complex dependencies, aiding in recognizing patterns and predicting eruption end timings. We have designed the following modules to execute this project. The first module is upload seismic dataset. Using this module, we will upload the dataset to application. The second module is preprocess dataset feature extraction. With this module, we will convert non-numeric values to numeric, and we will convert dataset into normalized format, and we will split the dataset into train and test sets. The next module is run SVM algorithm. Using this module, we will train SVM model with preprocessed dataset. Similarly, in the next steps, we will run random forest algorithm, logistic regression, and Gaussian process classifier on preprocessed dataset and get the accuracy of the models. The next module is all algorithms accuracy graph. Using this module, we will compare the accuracy of all the models. The next module is prediction eruption. Using this module, we will upload test file and then application detect eruption activity from that uploaded test data. The last module is ROC curve graph. Using this module, we will plot the ROC graph for all the algorithms. Execution of the project. To execute this project, first we have to open the code folder. This is the dataset folder in which I have the required dataset. This is the dataset, this is the test data. So in this dataset, the first row has the column names and these are all the rows. So this dataset contains seismic magnitude, and if its value greater than 6, then it will consider as volcano is about to erupt. Close this dataset. This is the Python main code file. This is the run.bat file. Instead of executing the project in command line interface, we have created this Windows batch file. Double click on run.bat file. This graphical user interface will be opened. With this, we are interacting with the program. Now click on Upload Seismic Dataset button. A dialog box opens, select the dataset and click on Open. It confirms that the dataset is loaded, and these are the top 5 rows of the data. These are bottom 5 rows of the data. And we can see there are 23,412 rows in the data and there are 21 columns. Now click on Preprocess Dataset Feature Extraction button. We can see previously we had non-numeric values in the data, and after pre-processing there are no non-numeric values. And the dataset contains 23,412 records. After splitting the data into train and test sets, now we have 18,729 records in train set and 4,683 records in test set. Now click on Run SVM Algorithms button. We can see in the text box the accuracy of SVM algorithm. And now click on Run Logistic Regression button, Run Random Forest Algorithm and Run Gaussian Process Classifier buttons. We can see the accuracy of all the models here in the text box, and we can see Random Forest is performing well when compared to all 3 other models. Now click on All Algorithms Accuracy graph. So in this graph, on x-axis I have the algorithm names and on y-axis I have the accuracy. We can see Random Forest is doing well. Close this graph. Now click on Predict Eruption button. A dialog box opens, select the test data and click on Open. In the square brackets, we can see volcano test data, and after square brackets, we can see predicted results as no eruption detected or eruption detected. When classifiers see magnitude value greater than or equal to 6.5, then it is classifying that record time as eruption activity detected. Now click on ROC Curve Graph button. So in this graph, on x-axis I have false positive rates and on y-axis I have true positive rate, and we can see logistic regression is performing well. Close this graph, and the conclusion here is the project aimed to understand eruption and timing in volcanic systems using machine learning algorithms. Using support vector machine, logistic regression, Gaussian process classifier and random forest, the most effective classifier was found to be random forest. This project showcases the potential of machine learning in classifying seismic time series data for predicting volcanic eruption timing and emphasizes the importance of using appropriate algorithms for accurate predictions.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.